Good morning, everyone. I'm Harini Ramakrishnan, Program Manager on the core networking team at Microsoft.
I'm Mike O'Gorman. I'm working in the Chief Technology and Architecture Office in Cisco Systems.
We are going to be talking today about the video broadcasting industry and how Windows DPDK helps overcome some of the throughput and the latency limitations in these video broadcasting applications encountered today. We are also going to take some time to summarize the status of DPDK on Windows and what we are going to focus on going forward. To set some context here, so the media broadcasting industry has evolved over the past many decades, so to speak, be it moving from black and white to color television or moving from standard definition to high definition in the past. But yet today, the video broadcasting industry is undergoing an unprecedented transition, getting ready to support high bandwidth media formats such as 4K and 8K in the future. Now, why are we talking about media broadcasting and what is this transition? So the media broadcasting industry is actually transitioning and is transitioning from legacy SDI-based interconnects and fabrics. So SDI is the serial digital interface-based interconnects that are available today. They're moving from legacy-based fabrics to standardized IP or an Ethernet-based infrastructure and workflows doing a lot of virtualization. This is still using the same SMPTE protocols. And what is the reason behind this motivation? What is the reason behind this transition? Essentially, the 4K and 8K high bandwidth media formats cannot be carried by the infrastructure that is available today. Essentially, there is just no capacity. So the bit rates are something that requires an updated, standardized infrastructure. And moving to an Ethernet or an IP-based network allows these media vendors to leverage the benefits of the cloud and allow them to scale rapidly and move to new technologies when there is a need that arises. Today we have Cisco's virtual media interface libraries. Now these virtual media interface libraries is a software toolkit that allows media applications that are making this transition from an SDI to an IP-based network. But the vMI stack as it exists today is optimized for legacy SDI workloads. Now moving into an IP Ethernet-based infrastructure, the problem that Cisco encountered was with respect to the data rates that can be carried over IP-based network. So say, for example, a HD-based video stream would only consume 1.5 gigabits per second, whereas a 4K stream would carry anywhere over 12 gigabits per second. Therefore, the vMI libraries needed an efficient path to the NICs and even to realize capacity at parity with what SDI has today. Now, as a result, Cisco, Microsoft, and Intel have been collaborating on this project to essentially bring DPDK to vMI libraries on Windows, and as a result, scale or overcome the throughput or latency limitations that was stemming from the Windows networking stack, so to speak. Now, Cisco vMI libraries are open sourced and available in a GitHub repository, and will be used by multiple end customer products and broadcasting solutions. Anything to add?
Yeah, so just to basically add, I think one of the challenges that the broadcast industry was having was as they were moving basically off of fixed equipment where everything is a fixed line connecting a camera to a video switcher to an appliance that actually does overlays or graphics overlays. If you've ever seen a broadcast studio, everything is literally hardwired. All of the equipment you need to produce that news show or that TV show is in that room connected by a series of cables. To be able to move away from that, they need to move to IP. The challenge is the SDI protocol that they've been using for 30 years now or more. Moving that to IP has some serious challenges. So there's obviously some networking challenges that needed to be solved. The reason working with Microsoft became so important is because we've been working with DPDK on Linux for quite some time, and Cisco and Intel have done a bunch of work around FIDO and how to get the most out of the Linux stack when it comes to networking. The challenge we have is all of the media vendors, for any number of reasons, are running on Windows operating systems, not Linux operating systems. And so when we actually showed what the technology of DPDK and vMI could do to these vendors. The problem is that they're running on Windows, and so when we heard that Intel and Microsoft were working together on actually importing DPDK to Windows, that opens up a whole new set of opportunities for the broadcast industry to now start getting similar, if not the same, performance out of the network that we can get out of a Linux stack. So it's a big change, big win. Just to talk a little bit about the standards itself. So when SDI, as I said, is that the protocol that's been around for over 30 years, describes how to transport uncompressed video across a wire. When we want to move over IP, the SMPTE standard had come up with a bunch of standards to actually describe how to carry SDI over IP. Again, these are largely derived from the SDI standards that have been around for quite some time. They're based on the RTP protocol, and there's some very serious packet timing requirements that are in the standard that are going to become a challenge when you're trying to run through a generic operating system. So when we're running over a physical wire, those timings can be met by all of the physical hardware devices in the workflow, but when you move off of physical devices and move into an IP network, you start running into timing challenges. And once the industry started to play with SMPTE over IP, we started running into a whole bunch of issues around timing, around packet pacing, and when you want to interface existing legacy physical SDI equipment with the SMPTE standards and SDI over IP, you end up with an impedance mismatch where things don't always work and packets start getting dropped, which if you're in the broadcast industry, packet drops are a big no-no. A blank screen on a live television show means somebody loses their job. So things have to run just as reliably, if not more reliably, when we move to the IP standards. So what we were doing in Cisco when we started looking at this is that we had been working on a bunch of broadcast use cases. And so what we came up with was, how do we get the vendors in this space access to these types of interfaces? Now, the media vendors in this space are not networking experts, they're not IP experts, they're not Linux or Windows experts. They write graphics applications that basically process video frames coming in on an SDI card. So all of these physical boxes they have an SDI card that takes the SDI packets, turns them into a video frame, and they're doing video processing on those video frames and then putting them back out over the wire again. So in order for the industry to really be able to adopt this technology, we either had to explain to all of these vendors how to understand the networking stack, which was never a good use of anybody's time. So what we created was a layer basically from the hardware up into the applications that took the SDI protocol running over IP, converted into video frames, and basically presented their applications with a virtual SDI card. Now, the benefit of that is they can run on any computing device that has a network interface, and then they still basically, their applications don't need to change significantly, they just need to link to the vMI libraries, and now they get access to a bunch of APIs for processing those video frames, and then the vMI libraries take care of the underneath, the SDI over IP packet processing coming into the box and going out of the box. So if you look on the left-hand side here today, I talked about those studios, there is something called an SDI router, which is a very big physical hardware box where every one of those cables comes in. You can imagine the cable management issues in a broadcast studio. All of these cables have to come into an SDI router. That SDI router is taking care of routing those SDI packets from the cameras coming into the video switchers, into the graphics transformations appliances, and back into the screens, and then obviously transported back out again. Very, very fixed, very, very rigid, and not at all flexible. The whole industry, technology industry is moving towards cloud-based and network-based solutions. So in order to make that transition, we have to create this cloud framework where we said we can take the existing media applications, we can now scoop them up off of a physical box that has a physical SDI interface, put them onto an x86 server, running a bunch of software libraries, and then we can move those anywhere that they need to move as long as the network then supports the strict timing. And the idea here, of course, is that we want to be able to interface with legacy SDI gateways because these broadcast studios have invested a lot of money in equipment over the years. They don't want to turn that stuff off and go for something completely new. So there's a whole transition about how do you get packets from a physical camera into an SDI network, run through an IP network, process those packets, maybe put them back into a physical SDI gateway to come back out the other side. So there is a whole bunch of transition where the old and new technologies need to work together. So there's a bunch of, as we said, strict timings within the protocol itself that need to be adhered to. And so the vMI is a software layer that takes care of those timings. So do you want to talk a little bit about some of this?
Sure, yeah. So I think the real highlight here is the fact that with respect to video processing capabilities, now with DPDK, they are able to now saturate a 40 gigabit link with almost 25 HD streams, whereas in the past, before DPDK came into the picture, they were limited to only about 5 HD streams, representing about 8 gigabits per second. So even if you did have a 40 gig card, they would still be limited or bottlenecked by the kernel-mediated I/O coming from the host networking stack. So as a result, now they are almost seeing a 5x increase in performance.
And so the whole point here is when we move into this environment, the software environment, the x86 compute you have, most of the computing power was being consumed with actually processing the packets inside the kernel, and the overhead of actually the software processing the packets coming in and turning them into video frames so the applications could process them means that most of the physical compute resources in the box were not available for compute functions. They were doing network functions. So obviously with DPDK and with VMI, we're able to bring that overhead way, way, way down. And now we're actually achieving similar performance graphs that we can get with FIDO on top of VPP, where now we're actually tracking the hardware limitations, and we can actually now start to scale linearly with what the hardware is capable of with a reduced amount of overhead of actually processing the packet. So for some of these tests, we've gone from consuming multiple cores in the box just to process the video frames down to, I think the video that we have has 5 HD streams, and all of the video or all the packet processing is being done on less than a core. So the rest of the compute inside the box is available for the video applications themselves. Yeah, so this is a video. I don't know how much value it's going to be, but we basically have a single box with 5 HD streams coming in. We're using our famous free open Big Buck Bunny, if anyone's ever seen that. Drives me crazy that we can't get something better, but anyway. The intent here is to show a single server processing those 5, this was one small box that we did the test on this week, running these 5 video streams in parallel. There's, I think, a 6-frame delay between each of them to show you that it's not the actual same feed. But again, all of the VMI processing and DPDK processing for this particular demo was measured to be running less than half a core. So the idea here is to be able to scale with the hardware, so as much network throughput as you have coming into the box, and then processing those video frames so that the applications can actually do their video transformations and put them back out on the wire using as a small amount of a CPU footprint as possible. Skip.
All right, so with respect to the code availability, so the open source VMI libraries for Windows using DPDK is available or will be available in a GitHub repository called Herrison, and there's a link right there to it. The Cisco's DPDK patch to support VMI libraries is also available in the 17.11 RC2 branch in the DPDK draft repository. So we invite you to download, build, and run applications using both VMI and DPDK on Windows and give us feedback so that we are able to constantly improve. The Herrison repository is expected to be updated anytime now with the updates for Windows DPDK.
And this really kind of marks the start of a bunch of testing work that we now want to go do. So now that we've got in VMI and DPDK working together on top of Windows, we can now start, obviously, scale testing this, stability testing this. As we said, for media use cases, this has to be rock solid, so there's a bunch of testing that needs to be done to make sure that we don't introduce any instability into those video processing environments. But we're now going to actually start in earnest some serious scale testing and finding out how far we can actually push the limits of the software and how much video we can process through a single box with the smallest amount of CPU overhead as possible. So we're going to start that work, and we'll start announcing that through the community over the coming months so people can actually start to see some of the numbers. We're working with a bunch of video vendors in this space already. We've been attending the broadcasting conferences, the NAB and the IBC for the last 18 months. Talking about what we're doing in this space. There's huge interest from a lot of the media vendors. They want to make this transition, but again, they're looking to the industry to provide them the tools to be able to make this so that they don't have to understand the underlying implementation details of those protocols. And so what we're trying to do is partner with some of the big vendors in that space. We're talking and having conversations with people like Deltacast, Ross Video, Kyron Hego, who all have Windows applications that they want to move off their physical boxes and basically become untethered from SDI cards and move to a virtual interface so they can actually sell their software as a software appliance that can run in anybody's data center and process the video frames with the guarantee that they'll get the same performance, if not better performance, than they're getting over physical SDI.
Just a note to add here, the Intel pole mode drivers that are used in this setup is also available in the draft repo for consumption. All right, this is just to summarize the current status of where we are with DPDK on Windows. So last year, this time at the DPDK Summit, we announced availability of the DPDK draft repository announcing Windows support, and we demoed over 70 million packets per second. Ever since then, now the Windows draft repo has been updated to align with the 18.08 public release, and we have the 17.11 branch and the 18.02 branch that is validated with both Windows Server 2016 and Windows Server 2019 with Intel 40 gig network adapters. And the essential libraries and the applications that are available in the repo have been known to function well on Windows. Now, Intel supports pole mode drivers, as you all know. Now, Windows pole mode drivers from our partners at Chelsea, KVM, and Broadcom are also under active development now and are expected to be available in the repo really soon. So going forward, I want to dwell for a moment and focus on where we are, where we want to invest or where we want to focus our energies on with respect to bringing DPDK support on Windows. So our first order of priority is, of course, the upstreaming of the DPDK draft repo to align with the main Linux Foundation maintained repository. So I would urge you to expect phased upstreaming of patches through the next year, through 2019. We have started taking baby steps towards that, and you should have seen a patch already submitted towards that goal. We are always also investigating alternative compiler support. For instance, today you need the Intel ICC compiler to compile the DPDK repository, but going forward, we are investigating support for Clang. We are also looking at a more secure multi-user, multi-process driver model to expose the NIC to the user mode applications. Please stay back for the upcoming session with our colleagues at Microsoft and Intel, and they'll be diving deeper into this particular driver model. We also want to make sure that the DPDK libraries and APIs are fully functional on Windows, which means that they are validated and performant. With respect to future investigations or longer time goals, so one of the things that we are looking at is support for DPDK in a Windows VM. So once we are able to stabilize DPDK on a host, on the Windows host, we want to bring this or extend the support into a VM, first using first over the direct device assignment and then using a guest VF. Also, like in this video broadcasting space, we have received a lot of interest and questions around pacing requirements and timing requirements, as Mike has been talking about. So that's also an area of interest and something that we have started looking into, what these requirements mean and what that translates to us from the Windows OS perspective. We are also looking at code isolation and reservation and what APIs are available or can be made available, so as to kind of leverage the code isolation with the Windows scheduler. So that's where we are with respect to future investments and direction. Here, I just wanted to take a moment to thank everyone that has contributed to this project. So there is, so Mike is based out of San Jose. We have a Europe team from Cisco that has been active participants and contributors of this project. Thierry, Andre, and Axel. From Intel, of course, we have our Intel team right here, helping us through this entire project. Thanks, Ranjit, Manasi, Elizabeth, and everyone else. From Microsoft as well, I would like to thank Jason, Omar, and Jeffrey who have committed resources into this project. So thanks, everyone. This is really a joint effort from a lot of partners here. Any questions, please feel free to reach out to me or Michael over email. Our email addresses are right here. And before Q&A, please download the Windows DPDK app draft repo and then test it out and give us any feedback that you have. It'll be super helpful.
Yeah, well, I mean, I said on the Cisco side, on the vMI side, obviously it's been an in-house effort for about 18 months to get to this stage of stability. We're very interested now in putting it out there to the community to see if other people are interested in playing with it, giving us feedback, maybe contributing to it. There's still plenty of work to be done. There's potentially other applications that could be used for the vMI library itself could be used. One of the interesting ones is that traffic pacing, where the actual SDI standards expects packets to arrive at a specific interval between them. There's not a lot of use cases out there, but video does need specific, strict timing about when packets arrive because most of the physical SDI gateways have very short buffers. So there's potentially other ideas for where we could take that library beyond just media use cases, but right now, as I said, we've been focusing on the media because there's some serious hard problems to solve in the media packet pacing. But again, we're interested in other people's ideas about where to take that library and other potential applications for the software.
All right. We'll be joined by Intel folks as well if there are any questions. So.
Yep.
All right.
Hi. So which are the hardware offloads that you are more interested in from the smart NICs or the NICs that you are using? And which other helps from the network cards could be useful for you? And the second question is this network just being used for the media processing, or is also shared with other network stuff?
So the first question is about what kind of help could we get from smart NICs?
Hardware offloads that you are using now, like LSO or LRO?
So there's a whole bunch of stuff. I mean, I think we could have a separate discussion around, what kind of support from the NICs themselves could offload some of the functions. One of the challenges, of course, is if we depend too much on smart NICs in this case, then again, you're moving to an environment where this software will only work when it has certain NICs inside the system. So we're trying to move to pure cloud and give people the ability to be completely decoupled from the hardware and the hardware requirements other than CPU and memory. And network throughput rather than network functionality in the hardware. But there are definitely some vendors actually out there looking at putting in some of this type of functionality actually into NICs so that you can actually have a virtual SDI interface built into your network interface as well. So there's a whole bunch of discussions I think that the community could start having around that, I think, over time. I think the second question you were asking about, are there other things running over this network? Is that what you were asking?
Yeah, because you are, for example, for this kind of deterministic processing of the packets that are coming. So you need to.
So I think we've been working with a bunch of big broadcasters in the US and in Europe over the last 18 months around how they're going to consume these types of technology. I think it's fair to say initially these networks are probably only going to run broadcast workflows until there's a certain amount of confidence and faith built up in the infrastructure. The goal eventually, of course, is to be able to get to a stage where there isn't a separate broadcast network from the rest of their IT network, where in theory both traffics could flow over the same network. But I think there's probably some way to go to prove the technology before broadcasters will start, putting more things on their network. But it is something that they're looking at. We're having, as I said, from a networking perspective, lots of conversations with the IT teams and the broadcast teams and these big broadcasters. And at least from an architecture, they want to have the same network architecture. They may run and operate separate physical networks for the reasons of having, no interference on their broadcast network versus on their IT network. But they are looking at trying to unify their architecture so that they can at least be the same, and then they can start experimenting with how much other traffic can coexist on that network. But for now, I think most of the testing that's been done is obviously just the broadcast workflows for now.
Thank you.
Any other questions?
You mentioned some of the requirements about timing and reliability, like not being able to lose a single packet. Can you go into some of the technical aspects of the work that you did to meet those guarantees?
There's a couple of things. There's a couple of ways of solving that. I mean, obviously, over an IP network, you can drop packets. There's two ways of looking at the problem. One is you try and harden the infrastructure so to make sure from a networking perspective that you're not dropping packets. One of the challenges that we have is when we take these SDI packets and put them back into an SDI gateway, sometimes the physical gateway will drop the packets because their buffers are not big enough. So what we found was we were seeing a lot of situations where when the traffic's going from IP back into SDI, we were seeing packet drops on those physical interfaces. So that's where we came up with the concept of putting a pacer in the software. So right before the packets actually leave the IP network and go into a physical SDI network, we put a pacer on the egress to basically pace the packets coming out of the IP network so that we wouldn't saturate or overload the physical SDI gateways. Even if you go and solve all of those hard problems, you're still going to end up with a risk of having some sort of packet loss or jitter on the lines. We've done a bunch of work in Cisco on our IP fabric. We've actually made a bunch of extensions into our hardware, into the Nexus line, to allow for much higher control over things like jitter and quality of service, so that you can run video workloads over a traditional IP network. So there's some physical boxes that we have that are actually tested and to higher standards of QoS and jitter flows that are that we're basically targeting at some of these media use cases. And then the third thing, of course, really is that for any of these use cases, because you're running in a virtualized software running in the cloud, you're always going to want to have a backup. So we end up, broadcasters, any broadcaster is going to have at least two parallel streams. So if one of the infrastructure starts to experience any sort of problem, you want to be able to do frame accurate switching over to the second set of infrastructure to make sure that you can get that, and to be able to stitch those together at the egress going back out into the broadcast infrastructure to make sure you can actually, you're joining the packets on a frame boundary as opposed to on an IP boundary. So there's a bunch of work that's been done in that space to try and solve that, both in the hardware, in the software, and then just in the way you deploy those types of workflows by always having, backup streams running from the cameras into two separate infrastructures, and the ability to detect when to switch over between them.
You mentioned that you're running on a general purpose operating system too. Are there any challenges on that side?
Sorry, could you?
You mentioned that you're running on a general purpose operating system now. Are there any challenges on that side?
Well, I mean, that was the challenge. When you're running on a Windows machine and you're virtualizing, the operating system overhead becomes a bottleneck, and the interrupts inside the operating system start to get in the way. So obviously, when we heard that Intel and Microsoft were working on DPDK, we know that we can remove the operating system overhead. The application, the media processing application itself, has some latency, obviously, because it's processing the video frames and transforming them before it puts them out again. But at least from getting the packets into the box and out of the box, we're trying to remove the uncertainty that the operating system provides.
Any other questions?
Okay, we'll be around for a few more minutes at the back if you guys want to come over and talk some more. And as I said, we're very interested in finding out if people want to contact us and kind of get involved in some of the efforts and know more, and maybe even contribute some work to what we're doing.
Okay. Thank you.
Thanks, everyone.